Okay, today we're going to be looking at merge sorts. This is the second of the three sorting algorithms that we need to consider as part of the OCR J277 specification. First of all, three quick questions just to recap some prior learning. What is decomposition? What is abstraction? And what is pseudocode? I'll pause and I'll give you a chance to have a think through those. If you need to, you can recap by looking at prior lessons or videos to support you with this. So specification content, as previously mentioned, standard sorting algorithms, we're looking at bubble, merge, and insertion. We're going to be looking at merge sort today. Requirements again, so understanding the main steps of each algorithm and the prerequisites of an algorithm, apply the algorithm to a data set, and identify an algorithm if given the code or pseudocode for it. Now, it's worth commenting and mentioning because there are some technical elements to this that aren't necessarily required for you to be able to do at GCSE. So with that being said, I'm going to show you the pseudocode and the Python code for a merge sort, but it is not required for you to be able to remember this or to be able to replicate this as part of the GCSE specification. It's just so you can see a side-by-side comparison of bubble, merge, and insertion as we cover all three of the sorting algorithms. So merge sort then. So merge sort is a highly complex algorithm. It's much, much more complex than the bubble sort that we looked at previously. However, with this increase in complexity comes an increase in efficiency as well. So whilst it is more complex to actually understand and more complex to implement, it does actually sort data in a much more efficient way. So there is sort of benefits to that complexity as well. When we're talking about a merge sort, the clue is given in the name and the idea that we are merging to sort our data, which means we're going to be merging lists in order to organize and sort our data. And we'll look at that in an example over the course of this lesson. You'll quite often hear a merge sort referred to as a divide and conquer method. And the idea is that we divide our list into individual lists and then we conquer the ordering of those. And we'll go through this, as I say, in an example. So here is an example. We're going to start with our dividing method. Now, this is the same list that we've used for our bubble sort, 3, 1, 4, 2. So you can see a comparison as to how efficient this is. The first thing we do is we find the midpoint of our list and we split it. So we end up with two sublists. And you can see that we've got 3 and 1 and 4 and 2 as our two sublists. We split that again and we end up with 4 sublists. And at this point, all of the elements are arranged by themselves. And this is the point we want to get to before we can start organizing data. Now, in larger data sets, this will take more steps. In smaller data sets, less. But generally speaking, it's a case of repeating this process until you get to a point where all elements are by themselves. Now, if you have an odd numbered list, so for example, you started with 5 elements, you would find that you would have a point where when you're in your first stage of splitting, there would be an element by itself already, although that would just continue to flow through. So now that we've got our sublists, we can start to consider conquering our lists. Now, the way that we conquer our lists is we start to compare our sublists together. So in this scenario, I've highlighted in blue and in sort of this orange pastel color the comparisons that were made. So on the left-hand side, we've got a check to see if 3 is greater than 1. On the right-hand side, we've got to see if 4 is greater than 2. And if that is the case, obviously, the data gets pulled down into sublists. So this is where it starts to get merged. And it gets merged in order through those comparisons. Now, when we get to a point where we have, in this example, 2 sublists, we're now going to start to compare the first elements of our sublist. So if we look on the left-hand side, in the blue sublist, we have the number 1. That will get compared with the first element of the sort of pastel color of the 2. So is 1 greater than 2? No, in which case 1 comes down. And then 2, and then we start to compare, is 3 greater than 2 because we're moving through our sublist on the left. And then we compare 3 with 2. We then compare, is 3 greater than 4? And then 4 comes down. And we get to a point where we end up with our merged list, which is made up of our sublists. And you can see on screen an example of that. There's no further sublist, and therefore the computer can prove that the data is in a sorted manner. So the merge sort algorithm. So the first point, split the list in half repeatedly until it's into individual lists, or each element is on its own. We then compare the first element in all of our lists, or both of our lists, and we start to merge them. We put the smallest into a new list, we compare the next element of our list with the second element of list 2, and we kind of repeat that process. It's a lot easier looking at it from a perspective of the worked example within this presentation. Here's the pseudocode for the merge sort. Now, like I said, it's not a requirement that you need to know this. This is just more for a point of reference. I've annotated where appropriate on this pseudocode so you can see exactly what's happened. And I'll pause so you can have a pause on the slide, have a read through. And then that pseudocode I've converted into Python code, just as an example here. So this is the working Python code if you wanted to type out the code, and you'll see the output of this program. Certain few things to consider then with a merge sort. So firstly, as I mentioned at the start of this presentation, merge sorts are not that straightforward to understand and not that straightforward to implement. It's slightly more challenging than perhaps a bubble sort. Merge sorts are memory intensive because at each stage of the merge sort, you're having to remember several sublists. So you could be in a situation where if you've got a large data set, there's lots of data that you're having to store every time when you're carrying out of your merge sort. And the merge sort, that although with all of these sort of considerations, is in fact the most efficient of the sorting algorithms when we compare with bubble, merge, and insertion sorts.